Hi, and welcome back. In this video lecture, we'll talk about the MPC stability theory and we'll state the main results. Let's start with an overview of the MPC problem. What we do in MPC is that at every sampling time, we measure the state of the system and we solve a finite horizon optimal control problem. This is denoted by P subscript n uppercase of x. Here x is the current state of the system which we assume we can measure. N uppercase is the prediction horizon. The problem consists in minimizing a total cost function, which is written as the sum of stage costs plus the terminal cost Vf at the terminal state xn. Vf, where the subscript f stands for final, and Vf will be attracting a lot of our attention. The problem is solved subject to the system dynamics. The state constraints xt belongs to x uppercase, ut belongs to u, which are the input constraints, as well as the terminal state constraints xn is inside xf, and the initial condition x0 is equal to x. By solving this problem, if we can of course, we obtain an optimal sequence of control actions, which is denoted by u boldface star n of x. Of course, the optimal sequence depends on the initial condition. Note that the sequence of control actions is denoted by u boldface, whereas individual control actions are denoted simply by u0 star, u1 star, and so on and so forth. Now, from that sequence of control actions, we select the first one, u0 star, and we apply it to the system. Recall that u0 star is the same as kappa n star if we use the dynamic programming notation that we introduced earlier. So we apply that control action to the system. We can simply discard and forget about the rest. And the closed loop now, system dynamics, becomes xt plus 1 is f of xt, comma, u0 star of xt, or kappa n star of xt. Let's see now what we expect from that MPC formulation. Suppose that the regularity assumptions R1 to R4 are satisfied. MPC computes control actions by solving an optimization problem. By solving the optimization problem Pn of x. It is a parametric problem. At the very least we should expect is the following property number 1, that if we can solve the problem now, we should be able to solve the problem afterwards. So once feasible, always feasible. Let's read it out. If Pn at xt is feasible, then Pn solved with parameter xt plus 1 must also be feasible. So if at the current state I can compute a sequence of control actions, an optimal sequence of control actions, and I take the first control action, I apply to the system, and from xt the state becomes xt plus 1, then at that new state I must be able to solve the problem again. Equivalently, we can say that x uppercase n, xn, the set of feasible states, is positive invariant for the MPC controlled system. For the system xt plus 1 is f of xt, comma, kappa n star of xt. This is the MPC controlled system. If you don't remember the definition of xn is the set of feasible states, and you can find the definition in handout 6, pages 3 and 4, bottom of page 3 and page 4. Now this property, that is the minimum requirement we must have, is known as recursive feasibility. So once feasible, always feasible. Recursive feasibility implies that all constraints are satisfied. So x belongs to x, u belongs to u, and we can find also, most importantly, we can find at every time instant, and starting from the current state, we can find the sequence of control actions, and that sequence satisfies all of the constraints of the problem. In addition, we need the origin to be attractive for the MPC controlled system. And we need it to be attractive over the set of feasible states xn. It is a bonus to require that the origin be asymptotically stable. So this is kind of a luxury. We might have it, we might not have it. Sometimes we will not be able to prove asymptotic stability. So that's why we call this requirement a bonus requirement. So the typical requirements are that the formulation we will come up with must be recursively feasible, and the origin must be attractive for the controlled system over the set of feasible states. The stability assumptions we use in MPC are the following assumptions. First of all, the regularity assumptions, R1 to R4. Second, we have the attractivity assumptions we have stated previously. I will show the attractivity assumptions in the next slide. So A1 to A3 must be satisfied, and there is one more requirement, and this is the following, that VF, the terminal cost function, which is a function from XF to R plus, so this notation here implies that VF is non-negative valued, it gives non-negative real numbers. So this function must be continuous. At 0 it must be equal to 0, and most importantly, and this is something that we need to remember, VF of x is above TVF of x, and this property must be satisfied for all x in the terminal set XF. So this condition involves both VF and XF. You see, this is annotated as TC, which stands for terminal condition. Indeed, it's a terminal condition in the sense that it involves the terminal ingredients of the problem, namely VF and XF. It doesn't make much sense now at this moment, but it will turn out in a little while that this is exactly what we need to be able to design a properly stabilizing MPC controller. So let me state the regularity and attractivity assumptions and the terminal condition in one slide. So the regularity assumptions are that the cost functions are continuous, so L is a function that you see is non-negative value and continuous. VF, the terminal cost function, is non-negative value again and continuous. The second regularity assumption is that the dynamics F is continuous. R3 is that the sets we have, X, U, and XF, are non-empty and closed. And the last regularity assumption is that either the set U is compact or the growth of the cost function is controlled by the norm of U, or that L, if you like, we can write it like this, that L is above a k infinity class function of the norm of U, the magnitude of U, which means that the farther away or actually the higher the magnitude of the control action, the higher a lower bound we should have on the cost function. Such assumptions are typically satisfied, all these assumptions, the regularity assumptions, are typically satisfied in all meaningful MPC formulations that we have in practice. Now then, the attractivity assumptions. First of all, the origin 0, 0 must be an equilibrium point of the system. Second, X and U must contain the origin. So the origin is a point where we can be, it is allowed, it's feasible, it is admissible, it is an admissible point. And third, the cost to be at the equilibrium point must be equal to 0. In addition, the cost function L must be, the magnitude of the cost function L must be controlled by a k class function, k infinity class function, alpha L of the norm of X. But that's a technicality. Last and most important is that VF, the terminal cost function, is a continuous function, which is 0 at 0, and the terminal condition VF of X above or equal TVF of X must be satisfied within the terminal set xf for all x in xf. And we'll see how to use that in practice in a little while. Now let's see what we get if we have these conditions, if we have these MPC stability conditions. Let's see what we can guarantee for the MPC controlled system. So suppose that the MPC stability assumptions hold. Then, for whatever prediction horizon n, first, xn, the set of feasible states, is positive invariant for the MPC controlled system. So we have invariance. That's the number one requirement we stated earlier. Second, the origin is attractive, it is globally attractive for the MPC controlled system over the set of feasible states, over xn. So wherever, let's break it down, let's see what this means. Wherever you start inside xn, you will, needless to say, remain inside xn. You will not go outside of this set. You will remain inside xn. So all constraints will be satisfied. That's the invariance statement we have here. And second, you will converge to the origin, which is fantastic. The third property that we have here, the third result of the attractivity theorem, states a performance bound. We have an inequality that involves V infinity star. First of all, at first sight, this is a fantastic result. It's good that we have something about V infinity star, because it's impossible to compute V infinity star. This inequality gives that V infinity star is upper bounded by Vn star. So Vn star, the optimal value function of the problem we solve, is an upper bound to the infinite horizon problem. It is worse than the infinite horizon problem. This is one observation. It is a higher cost than if we could solve the problem up to an infinite horizon. And the second observation is that by solving this finite horizon problem, we obtain a controller. And this controller is precisely kappa n star. This is something we can compute. Now, if we take that controller and we plug it into the infinite horizon cost, which is the sum from time 0 to time infinity of the stage cost L at xt, comma kappa n star of xt, that infinite sum is the infinite horizon cost, but not with the infinite horizon controller, but with a controller that we obtain by solving the finite horizon problem Pn. So if we take the controller we have, kappa n star, and we plug it into the infinite horizon cost function, we will have an infinite horizon cost which is above V infinity star. It is above the optimal cost, of course. It is suboptimal. This is not the best controller. Kappa infinity star would be the best controller. So it is above that, but it is below, it is bounded above by Vn star. And the last property comes from the monotonicity property of the dynamic programming operator, and states that as we increase the horizon, we will be getting a cost function which is below the one we have. So Vn plus 1 star is less than or equal Vn star. So to put it differently, the more the merrier. So the higher the prediction horizon, the lower the value function, the lower the optimal cost we will have. And there is a second beautiful thing, which again means the more the merrier. As we increase n from n to n plus 1, the feasibility set, the set of feasible states, increases. So xn plus 1 is a superset, can be equal, but it can also be larger. It is not smaller, certainly, than xn. So using a larger horizon, we have a larger domain, we have a larger set of feasible states. We can control more states, to put it differently. and we have a lower cost. The proof is there if you would like to study it by yourselves, but it uses very simple arguments. Now, of course, if we are after global asymptotic stability, we need to impose some additional requirements. Suppose now that, same as before, we have the standard MPC stability assumptions. And we have the following, which are additional assumptions. First of all, XF, the terminal state, the terminal set, XF, contains the origin in its interior. So as a counterexample, if you take XF to be equal to a set containing just the origin and nothing more, then this set is not empty, but it doesn't have an interior. So that's not the case, all right? You need a set that does have an interior. It looks like a bowl or, I don't know, a rectangle, a box, something that a full dimensional object that has an interior. And the second requirement is just that function VF that you will choose must be, the growth must be controlled from above by a certain k infinity class function of the norm of x. So it shouldn't grow much faster than the norm of x, and this should be true inside the terminal region XF. Typically we can choose a function VF that satisfies this assumption. For instance, if you take VF to be a quadratic function, then automatically you can see that this inequality is satisfied, especially as we want here, it is satisfied within XF. So if these additional assumptions hold, in addition to the conclusion of the MPC attractivity theorem, the four things we presented previously, the origin is also globally asymptotically stable for the MPC control system over Xn. And, in addition, Vn star, as we take n to infinity, converges to V infinity star. So we have a convergence of the value functions to the infinite horizon value function. And this, needless to say, is reminiscent of the whole discussion we've had previously about the convergence of value functions in the context of dynamic programming recursion. Let us now give an example of how we can design a stabilizing MPC. So let's say we have a linear dynamical system. xt plus 1 is some matrix, let's call it A, xt plus some other matrix, let's say BUT, AXT plus BUT. The system is subject to some simple constraints, like xt must be between -2 and 2 in every coordinate, and ut must be between -1 and 1. The stage cost is chosen to be the norm of x squared plus the norm of u squared. We can choose the terminal cost function Vf to be equal to 0 when we are at 0 and infinity anywhere else. We can write simply Vf bar of x is equal to the indicator of xf at x. We choose that terminal cost function. And xf is chosen to be a set that contains nothing but the origin. That is a very, very small terminal set. In other words, we require that at the end of the horizon, the state of the system must be exactly at the origin. We can verify by using the definition of the dynamic programming operator that T of Vf is less than or equal Vf, And this is the terminal condition of MPC that we stated previously. Now, if we go through the regularity and attractivity assumptions, we will see that each one of these is satisfied, and the terminal condition is also satisfied. V of f is larger than or equal T of Vf. Here we see xf, which is just one point, as well as the bounding box x around, you see, with a thick white line. The set x1 is simply the set of all states that can be steered to the origin in no more than one steps. And this is the set of all x in x, uppercase, such that there is a u in the set u, such that ax plus bu, namely the next state, is exactly equal to 0. The next state is exactly at the blue dot you see here. And this is just a line. Then the set x2 is the set of all states in x that can be steered to xf, to the terminal set, in no more than 2 steps. And this can be written as follows: it is the set of all states x, such that there is a u in the set u, such that the next state ax plus bu is inside x1. x1 is that line. Let's see this happening once again. x3 is the set of all states in x that can be steered to the terminal set xf in no more than 3 steps. And what is the definition? It is that this is the set of all states x inside the set x uppercase, such that there is a u in u uppercase, there is a feasible control action, such that ax plus bu, which is the next state, is inside the red set x2. So the orange set is the set of all states that can be steered in 1 step into x2, or if you want to put it differently, it is the set of all states that can move in 3 steps at most. There is a way for you to arrive at the origin. And the same way we define x4, which you see it is a bigger set. We define x5, which is the set of all states that can be, you have 5 whole time instants to reach your destination, which is xf. And we define x6 and so on. And you see that xf is a very small set. x1 is a larger set that contains xf. x2 is larger, and x3 is larger, and so on and so forth. And needless to say, all these sets x1, x2, x3, and so on are contained inside the big bounding box. Let's stick with a horizon of 6. For an MPC control system with a horizon of 6, we have that the closed loop system looks like that. xt plus 1 is axt plus b times kappa 6 star of xt. Please note here that this is not a linear system, because kappa 6 star is not a linear function. And why is that? This happens because we have constraints. So the presence of constraints gives rise to a non-linear controller. Kappa 6 star is non-linear. How does it look like? We don't care how it looks like. This is the solution of an optimization problem. We know how it looks like. I'm just not telling you because it's not relevant here. Just keep in mind it's not a linear function. And we have that x6 is positive invariant. We have this from the attractivity theorem. We have that the origin is globally attractive over x6, and we also have the performance bound v infinity star is bounded above by the infinite horizon cost function using the finite horizon controller kappa 6 star, and this is again bounded above by v6 star of x. And you see here the red line, we have started from a corner point, an extreme point of x6, and step by step we converge gradually to the origin. We can see the same in by plotting x against time and the input u against time. x1 is the first coordinate is the green line, the second coordinate x2 of the state is the pink line. We see the dashed line, which is x max. We see the u minimum here, which is -1, and we see that the control actions at the beginning are equal to the minimum possible value, which is -1, and again we don't have, at any point we don't have any constraint violations, which is good. It is excellent. So we have both a convergence of the state towards 0 and absolutely no constraint violations. Here we see the value function of the MPC with different horizons. So we see with horizon 6 and with horizon 10 at different points as we simulate the system in closed loop. And of course we know from the theory that V10 star is below, or at least no larger than, V6 star. So we see we have a lower cost function if we increase the horizon. In particular, V6 star is no larger than, is no less than V7 star, V8 star, and so on and so forth. And the lower you can ever reach is V infinity star, but unfortunately we cannot in most cases solve the infinite horizon problem. Now, a few observations we can make here is that, first of all, admittedly, the terminal set xf, which is equal to a set that contains just one point, is too small. I mean, at least we should try to think of a way to design a larger set xf. Why would we want a larger set xf? Because if xf is a larger set, then xn will be larger, so the domain of the problem. And this is very important because xn is the set of states from which we can control the system. We can only control the system inside xn. If we go outside, we will not be able to solve the optimization problem. It will be infeasible. xf does not contain 0 in its interior. It contains 0, so we have attractivity, but it doesn't contain 0 in its interior. So we cannot use the global asymptotic stability theorem we have to claim that that global asymptotic stability is satisfied here. Now, in the next video lecture, we will discuss how to come up with alternative and hopefully better designs for our MPC problems. Thanks very much for watching, and take care.